So this work, I'm really happy to talk about it. This appeared to a paper that was in the most recent ESOP, and it is joint work with my student Pratim Chowdhury and our collaborator Harley Eads. And Pratim and I are at Penn, and Harley is at Augusta University. Okay, so what am I talking about? Okay, so I want you to start thinking about type systems that track dependency. And what I mean by that is it's something that looks like this, right? So imagine we have an arbitrary lattice. So in this particular example, I have a lattice with 3 elements. I have a low, a middle, and a high. And what I want from this type system is I want the type system, if I've annotated the variables in the type system with these lattice elements, and then the judgment itself has a lattice element, right? I want to make sure that the type system is going to ensure that I'm only depending on things in my context that are equal or lower than the lattice element to my type system, right? So here, this example, this works because Z is middle, X is low, so I can use Z and X in lots of different ways, but I can't use Y, which is a high security, right? And so if maybe this is not the form you've seen it before, but this should be familiar perhaps to you. You might have seen similar systems. And an important property that I want a system like this to give me is one that I'm going to call non-interference from the security types world, but really it's sort of non-dependency, right? That if we, in our context, we have X that has some level L1, and we type check a term at level L2, if L2 is not greater than or equal to L1, so if L2 can't observe L1, then this term B can't really depend on X, right? And I'm going to make what depend means a little bit more formal in a little bit, but this is the intuitive idea of what I want to get from the type system. And like I said, you've probably seen things like this. So this is similar to type systems for security types, for non-information flow. The type systems I'm working with are going to be related to DCC, the Dependency Core Calculus. There's another similar one to DCC called the Ceiling Calculus by Shikuma and Igarashi. These are different ways of setting up type systems that track this kind of dependency.
So this is dependency, it's the terms depending on.
Yes, this is just tracking the dependency of terms depending on.
As opposed to dependent types where the types might be depending on.
Yeah. That's why I have 2 Ds in the name of the calculus we're going to get to.
Could the remote people hear me?
Oh yeah, I should have repeated Sam's question.
Well, just come in. Can you hear me?
Just about, yeah, it's fine. It'll be good if Stephanie repeated, because it'll be just more advice.
Remind me several times.
Sorry, I was muted, but yeah, repeating the question. If Stephanie can repeat the questions, that will be helpful.
Okay, I'll try to remember that. Okay.
Question, sorry?
Yeah.
Is my going to say that it's tracking non-dependency rather than tracking dependency? Right?
Yes, it is. Well, so yes, OHADAS, are we really just tracking non-dependency? And that's true, right? Because nothing is requiring the system to actually use variables in the context that are lower, right? It's just preventing the use of variables in the context that are unobservable. Okay, so what I'm trying to do in this work, right, is so we have a pretty good understanding of how dependency works in simple type systems, but there's not a lot of examples of dependent types that also include this kind of dependency tracking. And so what I want to do is to take that idea and put it in a dependent type system. And the reason I want to do that is I want to use that kind of dependency to explain this phenomenon that's known as irrelevance in dependent types, right? And so when we talk about dependently typed languages, we often talk about 2 different kinds of irrelevance. So I want to be clear that there are 2 things going on. And I want to use this mechanism to talk about both kinds of irrelevance. So we talked about runtime irrelevance. So when you have a program written in a dependently typed language, there are some parts, some of the arguments to your functions are only there for proving things, they're only there to get the program to type check. They really aren't needed to to execute the program. You can erase them before computation. That's runtime irrelevance. When you type check in a program, in a dependently typed programming language, you have to decide when two types are equal to each other. In a dependently typed language, you have terms in there. Some parts of those terms, you can ignore them when you're comparing for equality. That's compile time irrelevance. Right, so I want to use this kind of structure of a dependency type system to identify what parts of the terms can be erased and what parts of the terms can be ignored. Sometimes they are the same parts.
So you're going to use a matrix with a lattice with 3 points.
I am going to use a lattice with at least 3 points.
Right, so one's for runtime, one's for compile time, and runtime irrelevance, compile time relevance, and relevant.
Yeah, the other way around, or I couldn't hear whether you said irrelevance or relevance. I'll get to the lattice in about maybe 5 slides.
Okay, but the other thing I want to ask, maybe you'll get to this later, is will you relate this to quantified type theory, which can also deal with, I guess, runtime irrelevance, maybe not compile time?
At the very end, I have a related work slide where I try to put this in context, but I'm happy to also follow up with many questions about the relationship.
Okay.
It is related to, you're right, that QTT, quantitative type theory, is designed for runtime irrelevance. Okay, so to talk about this extension with dependent types, I want to make sure that I want to kind of get the structure of the type system, just the simple version, fixed and explain how it works and what the pieces of it are. And then I'm going to talk more generally about the extension with dependent types, right? And so just the first 3 things is just sort of like simply type lambda calculus with dependency tracking. This is the kind of language that we'd be able to do that judgment we saw on the first slide, right? And so as you can see, we have a label L, and it almost always is the same in these 3 rules, right? So we're always checking at a particular level L, and the thing we're checking is just what the labels of the variables are, right? So any variable that we use has to be less than or equal to L. And when we get to functions, we're going to be extending the context, but we don't really care about bound variables. Really, this is about talking about free variables, right? And so we're just going to use L for all the variables that we put into the context. So this is a little bit different of a dependency tracking type system that you may have seen. It's an equivalent formalization, and some prior work has kind of shown how different versions relate to each other.
We have a question from the chat.
Yes.
High level. You mentioned programming languages, but that the idea is equally applicable to other languages, such as hardware description languages, configuration languages. You thought about that?
I haven't thought about that. Probably. I hope so. Yeah. Okay, so this system, though, is not really that expressive because there's no way to change the level or talk about certain parts of the program being at a higher level that we've seen in other systems. And so what we want to do is kind of internalize this type system as a type, a graded modal type, where we're going to add a new type that's T, and it's annotated by a label L naught that's going to be sort of allow this language to talk about other levels. Right, and so we can have terms that talk about other programs typed at a different level, right? So we'll do this. So here's the 2 rules that talk about that graded modal type, right? So if we have a term that's type checked, so we're starting at L, and say we want to go up to some other level, L naught, right? So we'll join it to make sure that we're always going up. Right, so this isn't really going to give us a mechanism to talk about going down. It's only talking about going up. So we want to include maybe some high security data in our program. We can use this ADA constructor to just inject into that high security data, right? And that's going to create an element of this modal type, right? It's going to be annotated with a level that we've used to check A. And then the elimination rule, so it's called bind by a sort of analogy with DCC's bind. It's not the same structure as DCC, but it's similar. This is how we are going to eliminate. If we have an element with this graded modal type, and we have a context that wants to use the value, well, we're going to stick a variable in that context with the higher security level that then we can either use or not use, right? So maybe if L is lower than L naught, so say this is a high security value, we want to use it in a low security context, it can use it as long as it sticks it inside of some other protection box, right?
So that basically allow you to have high security data can sort of flow through a low security bit of the term, as long as when you actually read it, you're back in a high security.
Yeah. So Sam asked if this mechanism, this ADA, right, allows us to kind of box up high security data and allow low security programs to kind of push it around, but not really use it. That's exactly what's going on, right? And so this is kind of similar to how DCC is tracking it. We could also have a different sort of elimination form. So the Shikuma and Igarashi, instead of using bind, they had something called unseal. So they had the same introduction form where they box it up or seal it, and then they could unseal it. We can define unseal in terms of bind by just binding it and returning it, and that gives us an elimination rule that looks like this. That says you can unseal as long as you're in a context that can observe that result. And it's kind of equivalent, even if they're interdefinable. Right?
So
But here's good intuition about how to use this type. Yeah, Phil?
So the unseal rule seems very intuitive. It says you can get something at level 0 that's smaller than L, and you can still use it at level L.
Yeah.
That seems completely intuitive. The return, I don't quite get the intuition there, because it seems like their A could be at a level L that's higher than L0, and I can box it up to be at L0, and I don't understand that.
You're talking about what if L0 is less than L in the return rule?
Correct.
Right, and so we box it up at a higher level. So if L0 is low and L is
So
medium.
A might be high, right? A is a high security thing.
Yeah.
But I might pick L0 to be low. So it says I can take this high security thing and put it in a box that says this is the low security thing.
Yeah, but your L on the judgment in that case is still going to be high. You're still going to be in a high context. So you haven't really hidden anything at that point.
So what does it mean to say something has type T L0A? What is that L0 guaranteeing us?
That is telling us about what variables that A depends on, right? So all the variables that are used by A have to be at something that is less than or equal to L0.
And how does the rule guarantee that? Because the rule seems to guarantee that all the things used by A are at level L or L0.
I'm going to make this a little bit more precise when I prove a property about what happens in a minute.
Okay, I'll just let you know I'm still confused. I'm waiting to become unconfused, but I will silently wait.
Okay. Yeah, putting something inside of an ADA doesn't really count as using it. Right, that's sort of boxing it up for later. Using it is sort of like, if it's an application, we would apply it as a function, or returning it as a result of a function. But here, let me get to some of the properties, and maybe that will make more sense too. Okay, so this is sort of our base type system, and this is the type system that I want to use as sort of a core of a dependently typed system, right? But before I get to that, I want to talk about some of the properties of just this simple system, right? Especially in terms of that dependency property, that non-interference right? How do we prove that kind of non-interference reasoning? And to know that exactly what Phil asked, that how do we know what it means to say that high security things in your context don't have any influence on the result, right? And so to talk about that, I'm going to define first a sort of this labeled relation, right, that talks about when terms are related to each other up to some observer, right? So I'm calling this relation indexed indistinguishability, right? And what it's saying, and here this is, I really define this using a whole bunch of inference rules, but this is sort of the intuition behind those rules, right? And what this rule is saying is that here I have A and B, and if you have an observer at level L, they can't tell the difference between A and B. So there might actually be subterms of A and B that are different, but if they are different, they're going to be, you know, marked by one of these eta terms and marked at a higher level, or something that's not less than a level that's not observable to the level L that we are relating the terms at, right? So it's mostly just like this is syntactic thing, right? It's just, it's a lot like reflexivity, except that we're going to allow some parts to differ arbitrarily if they've been boxed out. And then we also, we're defining this with respect to a context as capital Phi. That's just talking about what the levels are of the variables in the terms. And we want the terms to kind of be consistent with respect to those variable usages. So that's what the second bullet is talking about. And that's, so even though this relation is not typed at all, right, it's still related to my typing judgment, right? So that you know, if I'm type checking a variable, or if I'm typing checking A at some level L, right, then the context that I use, the levels of the variables, in fact, that's the context that I need if I want to relate A to something else at level L. Right, and that part is there, so I can talk about how substitution works with this relation. Okay, so
Stephanie, that's really helpful.
Yeah.
The intuition I have now is that when you box something up,
Yeah.
you would box it with a level higher
Mm-hmm.
than where I am now, and that's fine as long as I never look inside the box.
Exactly.
Okay,
Mm-hmm.
now I've got the intuition. Thanks.
You could almost think about it as encrypting things that are in the box. That's like if you really are, if you really want to be certain that your observer L can't see what's there, but that's harder to generalize to multiple levels. Yeah.
You have an eta law for the box.
Do I have an eta law for the box? I do not.
Okay.
Right, or there might be one that exists. I haven't really thought about it.
If you unclear notation, you could probably easily get one.
Yeah, yeah. Okay, so we have this relation, and just to give you some examples of the relation. So here we have, I boxed up true and false. There, I boxed them up at high. A low observer can't tell the difference between true and false. So these two terms would be related in this relation. But if I had a high observer, they're not going to be related, right? Because the high observer could look inside the box and see that true and false are not the same, right? So this is my sort of basis that I'm going to use to define when things are equal up to some observable level, right? And this is not really a new idea. A lot of security type systems have this idea of defining an equality that's indexed by an observer level.
When you write F:(L) there, do you mean F:(superscript L) and then some type that you've not mentioned?
No, I do mean F:(L). This is not this relation is not a typed relation. I need the levels for all the variables, but I don't need their types. So I have a different.
This is a different relation. Okay.
Oh, no, so to see it's a phi, right, which is not a gamma.
Okay.
I've got another question.
Yeah.
So here you're demonstrating an example of boxing up at a higher level than the current.
Yeah, yeah.
Is it useful to go the other way ever?
Not really, no.
But the type system doesn't.
Yeah, the type system is fine with it if you do, but I don't think it's as useful. Okay, yeah, so right, it's kind of this is informal, right? Because it's not exactly the most relation because you got to get the phi right in the levels, right? But terms are going to be related to themselves, assuming you have the right context to describe the levels for the variable, for the free variables. Right, and it's going to be closed under substitution. I'm going to say exactly what that means in a minute. Right, but it's a good relation to kind of work with, to think about when things are right. And the really nice thing about this relation is that it's going to be closed under my operational semantics. So if I have an operational semantics, it's just a simple small step, term stepping to other terms, call by name. And it's going to, so if I have two terms that are related, and if the left side steps, then there is something for the right side to step to such that both results are related to each other at the same observable level. Right, so you can kind of, so this thing is closed. We can close this relation by the operational semantics because it respects it, right? And that's really what I want to do, right? Is because I want to close it by beta reduction so that I could use this relation as my notion of what definitional equality means in my type system, right? So I want to talk about ignoring certain parts of my terms when I'm type checking. I'm going to take this relation, close it by beta reduction. This relation ignores marked parts of my program. That's exactly the terms that I can that are going to be compile time irrelevant. Now let me just oh, and the other thing about this thing being respected the operational semantics is that we can use this result and then type soundness for the system to give us something that looks like non-interference, right? So what do I mean by that? If we have B that's type checked at a low level in a context that includes a high variable, and then I have two high terms that I've type checked at high, I could take X and replace it by A1 and evaluate, take X and replace it by A2 and evaluate. I'm going to get the same answer both times, right? And that's just going to fall out from these two, from this and from type segments.
Can I check my understanding of this, Steve? So before you introduced the eta and the bind,
yeah,
if you had this XHA, B type checks in terms of X,
yeah,
you'd probably expect that X wouldn't actually appear at all in B.
it would not appear at all.
Yeah.
Yeah.
Whereas
Yeah.
with the binder means it could do, but it would be underneath, and
Yeah.
you say you wouldn't see that.
Yeah, it could appear, but you're not allowed to use it.
Or well, if you did use it, then on the right hand side, the type would have been a higher level.
Yeah, yeah, exactly.
Okay.
Yeah. Okay, yeah, so this is what I was just saying, that we could use this to define now something that's like beta equivalence, except that it has this observer level associated with it, right? By just, taking an enclosure of this relation that we have with respect to beta equality. It's a definition of equivalence. It's not typed, right? So it's more like a pure type system, which uses an untyped definition of equivalence. Right, and here's what I meant by substitution. I just kind of want to make this kind of obvious or more concrete in terms of what substitution property this definition of equivalence has, right? So if we have two terms that are related, right, at a particular observer level L, and they have a variable that could appear one or both of them at some L naught, if that L naught is observable to L, then, and we pick two related terms at L, we can substitute them in. If L naught is not observable, we can substitute any two terms. Notice there's no preconditions on any one. Right, so the context and the level that I'm using is really guiding what things have to be the same and what things can be ignored when we're thinking about this definition of equivalence. Okay, so this is sort of the framework that I'm using and the pieces, and now I'm going to put it together in a dependent type system, right? So we're going to call this dependent type system Dependent Dependency Calculus, just to play off of DCC. It's got dependence in two different ways. So what is it? So it's a pure type system, right? We have this lattice of dependency levels, right, that go along with it, right? We're going to use those dependency levels in this dependent type system, and they're going to annotate pi and sigma types in this type system, right? And when I do it that way, right, what that's going to do is that's going to allow me to encode the graded modal type, right? So I don't need to have this graded modal type in my language anymore, because I'm going to get it from my sigma type, right? So if I pair up this label sigma with just a trivial value, that's going to play the same role as this graded modal type. And what that's really going to say is, if you think about how this label interacts with the sigma type, right? Well, that's what the rules for the graded modal type is. Okay, so I don't have the graded modal type. I'm going to define it using sigmas. Now, I said I'm going to I'm going to have an arbitrary lattice, but it's not quite arbitrary. There has to be some level in this lattice that is distinguished, that is called C, right? And this is going to be our sort of compile time relevant or comparable. C is sort of some element in the lattice that you pick out. The lattice itself can have as many elements as it wants. If it only has a single element, so bottom and top and C are all the same element, then we're just going to get a normal pure type system. But as we make more distinctions with our lattice elements, we'll be able to talk about more things. Right? And so what's going on with C? The reason we need to have a distinguished element C is that's going to tell us about how compile time irrelevance works. So we're going to use that as the observer of our definitional equality. Is going to be fixed at this lattice level.
There's an online question. Do you need the lattice to have the ascending chain condition? Repeat the question.
Do I need the lattice to have the ascending chain condition? I don't think so. I don't, not for any of the results that I've proven.
Okay. Thanks.
I have a proof and calc of all of the results of this work, which includes the axiomatization of the lattice, of what it means to be a lattice. So you can, at the end, I'll give you the URL if you want to check it out and see precisely what the requirements are. Okay, so we have this lattice. So it's good if we have 3 levels, because that can tell us about, we can talk about 3 different things happening, right? So this is just intuition for now, but like if we're thinking about what we need for runtime, we're going to type check using the lowest level. When we're talking about things that we need for comparing for type equality, we're going to be type checking at level C. And if we're talking about things that we don't need at all, either at runtime or for comparing type equality, then we'll use the highest level of the lattice. Right, just to kind of the lattice element that we put on our judgment is kind of making these level distinctions for us. Right, and another thing I want to say about the system is I've only proven sort of type soundness and got the non-interference result basically from the same way I just showed you, just in terms of the operational semantics, right? So these are pretty weak properties of the system, right? And so that's good because they apply, I don't really, like this doesn't have to be consistent, right? I don't need a lot from my language to be able to know that it's tracking dependency and that we can have compile time and runtime irrelevance. I mean, certainly it would be good to have more stuff, but it's just not required to make these distinctions. And my interest is more on thinking about adding these kinds of features to Haskell, which doesn't have a lot of, for example, is not a consistent object. Okay, so I'm using this lattice. Now let's start thinking about a specific lattice with only 3 points in it, top, bottom, C, and top, right? And so we're going to use it for runtime irrelevance. And when we say that, when we use it for runtime irrelevance, we're asking the question, what can we safely erase, right? And so we're going to type check anything that we intend to run at the lowest level, and everything else is going to be erasable, right? And what non-interference, or results about non-interference, that's going to assure us that we didn't erase too much, that everything that remained is only what we needed to actually run the code, right? And then for compile time irrelevance, right, when we're doing our type checking and comparing transfer equivalents, that question we're really asking is what parts can we ignore, right? And there we're going to type check parts that are comparable, and most at level C. The C is going to tell us that things are comparable, and everything else we can ignore. And there, in that case, non-interference is going to tell us that when we have this relation that says two things are equal, then it's consistent. And there, that consistent means we're not going to equate two terms with different head forms. We're not going to equate a pi type and a sigma type together. We can only equate types that have the same heads. Yeah.
Is there a presumption of the rightness that things that are irrelevant at compile time are definitely irrelevant at runtime?
Yes.
Repeat the question.
Oh, the question is, the way we set this up is if something is compile time irrelevant, I always get this backwards, right? If something is compile time irrelevant, it is also runtime irrelevant, meaning if we can ignore it while type checking, we can also erase it before running, right? But there will be some things that we can erase, but we can't ignore when we're type checking. Right. I tried to spend a little time trying to think about examples where we want to ignore it while type checking, but we still can erase it. I haven't really thought about that, right? And maybe we can talk about that, right? Because this is an arbitrary lattice, but, okay, so full disclosure, I did put in an assumption that would rule out that particular lattice. There's one more constraint that says that C has to be higher than anything that's not, or it's a choke point, right? I don't think I need that. It was just convenient to do it that way. So I think we could drop it.
I'm just sort of wondering, is there a,
But I haven't thought of a use for it.
is there, well, I was wondering if there's an example of a use case for the negative thing that Ian was asking about. Like, can anyone conceive of a world in which you have something that's ignorable while type checking and yet useful at runtime?
You could have something which maybe helps further execute faster.
Right, okay, it doesn't affect the types at all.
Some JIT compilation or something.
A sort of catalyst.
Well, one like size types, so you want to ignore the sizes.
At runtime,
Like there.
yeah. But does that really help at runtime? I mean, in a way that the semantics can observe the operational semantics. I don't know. Let's save this for later. But yeah, right. If it's just for efficiency, is that really? I don't know. Maybe. Yeah, I don't know. Okay, so let me show you some examples of what type checks in this system. Right. So here's our polymorphic identity function. So this is an example of a function with an argument that we want to both erase and ignore. Right, and so the polymorphic identity function says that for any type, you give me an argument of that type, I'll give it back to you. So the type argument is erasable and ignorable. The value argument y is neither. Right, you have to keep it around. I'm going to start doing some more examples. As I do more examples, just to simplify them, I'm going to stop drawing or stop putting the bottom labels on parameters, right? So if I just drop the bottoms, I'll only mark things that are ignorable or compiled or comparable, compile time relevant, but leave everything, most things you actually use when you run. So it's better to leave it implicit. Okay, so let's think about this polymorphic identity function a little bit more, right? So what's going on here, right? So since y is at bottom, we can use it in the body, but x, this y, bound by the lambda, it can be used here. This x bound by the lambda, it's marked at top, so we can't use it at all for this to type check, right? But what about that x bound by the pi, right? So in the pi, I've marked that x with top, but this top here, it's talking about the x bound by the lambda. It's not talking about uses of the x bound by the pi, right? Because if you could see, like, here this x, I'm using it in the body of the pi top, right? It appears twice. And so I don't want to make this be, I don't want this to be top. I want to be able to write the type of my polymorphic identity, right? And it's going to be relevant at compile time, right? And so really, when you see the label in a pi type, you need to think about it as the label of the variable of that function that has that pi type. It's not talking about uses of the variable in the pi type itself. Right. And when I type check ID like this is just, I think I said this already. When I type check ID like this, since I've given it this type, where we've marked that parameter as being top, that means I know just from the type of ID that I can erase its argument. And when I'm comparing maybe two applications of ID, right, to, ID A true to ID B true, I can ignore it. I don't have to look at them to decide whether these two applications, right? And the type is telling me that, or the type is determining when I have applications, what annotations I have to do on the applications. And then those annotations are going to determine how I do that equality. It's going to tell me that I can ignore these parts. That's the little.
So I find the last bullet point slightly surprising. Is the reason for that because you're not allowed to compare those two unless you already know they have the same type?
Yeah, I was surprised the first time I learned about compile time irrelevance that it could actually work, but it does, and it is true. It's not that this isn't the typed equality, even though, I mean, at the end, we're going to check that we're going to compare things that have kind type for equality, but we're not going to check that every subterm has equal comparable types as we compare it for equality. We don't look at that. But what's really going on is if we had screwed it up, something would not type check somewhere.
So, I mean, you might imagine that A and B must be full.
Yeah, exactly. For these terms to type check, right? We type check them somewhere, sometime. Not now, but sometime we type check them. And they're only going to type check if they were bool at some point, sometime, right? And so we don't need in this.
Right. So when let me put this differently. When type checking ID A true, you pay attention to A.
Yes.
But when at type checking time, we're checking these two terms for equality, then we don't need to check. Okay.
Yes, exactly.
Then my intuition is in sync with what you're saying. Thank you.
Yeah, yeah.
Supposing we're assuming there's no overloading. So it's harmless to say, yeah, true is true.
Yeah, yes. There's no overloading. There's very little in this calculus. Okay. Okay, so let's look at a bigger example of what this looks like if we have an index type like vectors. And here I'm betraying my Haskell that I think about everything in terms of Haskell. So I'm thinking about these vectors sort of GADT style, how Haskell would manipulate them. But what do I want to do? Right, when I have a vector, I don't want to store the parameters to the vector, right? When I have nil and cons, I don't want at runtime to keep around the length of the vector and the type of elements in the vector, because I have everything under the compile time. I know it from the type of the vector, so I shouldn't have to have it at runtime. right? So I want to be able to both erase and ignore length and type parameters for nil and cons. And in fact, I know this, I'm going to show you some examples with vectors. I'm not even going to write them, those parameters to nil and cons. I've already erased them from my head. But notice this again. In vector, I don't want to ignore or erase these arguments, right? And that's really important because I want a vector of length 3 to be a different type than a vector of length 5, right? When I'm comparing those two vectors for equivalence, I want them to be different types. I don't want to ignore their length arguments, right? And a vector of ints has to be different than a vector of bools, right? Right, and this is, and this last bullet is just reminding you that these tops annotating in and a, they're talking about the data constructors nil and cons and how they use their arguments. They're not talking about how in and a are used in the type of nil and cons, right? So, for example, nil is going to give me a vector. That vector, these are relevant, right? And so in and a can appear in relevant positions, right? Because this is really, it's not, I can use these in and a freely. Okay, so let's look at an example of a function over vectors that type checks. So here I have a vector map operation. I want this function. I want the length and the type arguments for the type of the function that I'm going to map over the vector. The lengths of the vector, I'm going to get the same length back, but I still want that to be erasable and ignorable, right? So, so the length and the type parameters in this function are also going to be irrelevant, and that works, right? So I take the irrelevant arguments, the function itself I'm going to use, so this is going to have to be a runtime thing. The vector I'm going to use, so it has to be a runtime thing. Pattern match it. I can return nil. If I have a cons itself, right? Since I'm doing this GADT-style, cons also carries a length that is the predecessor of n. But that's also going to be irrelevant. That doesn't have to get stored with cons. So when I pattern match it, I'm going to mark it as irrelevant in the example. But I'm just going to use it again as an argument to the recursive call and back to cons, back to irrelevance. So things work out. I can erase what I want from this function. And if I were thinking about when to VMAP applications were equivalent, I could ignore the n in A and B when I can compare. Okay. Here's another example, and this is an example which is going to motivate why I want to distinguish. So notice here on all the examples I've shown before, everything has either been bottom or top. I haven't really needed to use C in those examples to mark any of the things. So I haven't really pointed out arguments that I want to erase at runtime, but I still need for type checking. And that's going to show up here in filter. And this is a little subtle, but it is a motivation for distinguishing to have different levels, right? For a long time, I thought we don't need to have all that complexity, right? Things are either irrelevant or irrelevant. We don't even need to write them in the terms. We just erase everything. But then you can't really get what you want from this filter example. So let me explain how this filter example works and show you the kind of trade-offs that happen. Right. So what's going on with filter, right? So when you filter, so first of all, just assume we have a type of elements in the vector. I'm not really going to talk about it much, in a function that we're using the filter with. And now here's a definition of filter where we get a vector of a certain length with those element types. We're going to get a new vector. We don't know how long it's going to be because we don't know how many elements we're going to keep from the old vector. I could add in some information like the length is shorter than the input, but I'm not even going to do that. I'm just going to get a new length, right? And a new vector of that length. And here's the definition of filter. So I get in the length, the vector, I do pattern match. If the vector is an empty vector, the new length is 0, and I return nil. If it's a non-empty vector, then I look at F and see whether my predicate is true. If so, this is an element I want to keep in my result. So then I call filter recursively on the tail of the vector, right? Where the length of the tail, remember that's stored here in the columns, and I pass that in. And then I get a sigma, so I get a new length and a new vector from the recursive call. And then I can pair that together by incrementing the new length and making this new vector. Right? And then if the function is false, then I just call the function recursively. Right? And this is great. And then really nice thing about this version is that the sigma type, I can say that length of the new vector is irrelevant. I don't need to keep it around at runtime. But there's a problem. There's a reason I don't like this implementation of filter. And this is something that Richard Eisenberg pointed out to me about this implementation. What's wrong with this filter?
It's not parameterized on the app.
Oh, you can make it. Yeah, we can make it parameterized.
Not the recursive.
It's not tail recursive. Yeah, it's too strict, right? So if you're writing this in Haskell, if you think about the Haskell filter function, right, it's a lazy function, right? You only filter as much as you need, as you demand from the output of the filter. But this definition can't do that. And the reason it can't is because, right, when we do this pattern match here, right, we have to filter the entire vector before we can return anything. Right. So this pattern matching is a strict thing. Right. And he discovered this when he was thinking about existentials and Haskell. So an existential is kind of an example of one of these dependent sigma types where the first component is erasable. Right. But the only elimination form for existentials in Haskell, right, is this pattern matching. Right. And so that's a little, yeah.
If the end is raised, why not just return this? If you can't do anything with the length, you get that.
Yeah. If I can't, okay, so the question Bob is asking, if which is erased, I can't do what?
So you're returning a sigma type of M and then,
Yeah.
I mean, I just don't know the type of the whole thing.
Yeah, this whole thing is a sigma type.
But if the M is going to be erased,
Yeah.
and you can't do anything with it. So if you can know that, again, you have to measure the length of the vector.
Yeah, you would have to measure the length of the vector.
So, I wrote, no, maybe this is just for an example, but why not just return list?
Why don't I return list?
And that's the same thing. As
well, this is a vector where to know what the length is at runtime. Like, see, here, I don't need to actually have the length around.
No.
It's, yeah, I could return list, but that's a different type altogether.
Yeah.
Right, and in this one, I can just unpack it and pass it on to VMAP. I know that I get something that has the same length, even though I don't really know what that length is.
So it's the point that the type you have there is basically isomorphic to a list.
No, that's not really the point, right?
Yeah,
That's Bob's point. Yeah, that's Bob's point. Right. What if I had added a irrelevant proof that the length is smaller? Then it wouldn't be isomorphic to list, but we would still have the same problem. Yeah.
So you said that this is in Haskell when you have to filter a whole list.
Yeah.
I mean, I'm not sure that's going to be true because the pair, it depends on whether the M and V want a straight. And if you get back to filter used a pair, that just means you went far enough to find something, and it will give you a stack of I don't know yet. And you might laziness might save you a bit.
No,
I still see the problem. I don't know.
it doesn't.
No, you really have to go the whole way down.
Yeah, you really have to go down the whole way. Right, because it needs to, right, you need to know you get this, you need to know you get a pair. And really what's going on is the elimination form we're using for our sigma, right? We're doing pattern matching elimination, right? And what we want to do to have if we want to have a lazier definition of filter, we want to use first and second, right? So let's see what happens when we use first and second, right? Okay, so we're going to rewrite filter, the same code as we saw before, but instead of doing that pattern matching on the recursive call, right, I'm going to build up, in the case of the predicate is true, right, I'm just going to build up the length by just calling first on the recursive call, and then the tail by calling second on the recursive call, right? And this one is lazy, right? Because we're using first and second. But we've lost something, right? Which is now, if you look at the type, now M has to be around at runtime. And why is that? Right, so we haven't been able to mark M as ignorable or irrelevant, because if you think about it, when we do second, this is the type of second, right? We substitute first inside of its type. So if you look at Y's, its type is this sigma type. We're going to substitute first for M. And this is a relative position, right? We want vector, when we're comparing this for equality, we don't want to erase that first, right? And so we can't make this thing completely irrelevant, right? We need it to be around a compile time so that when we start comparing vectors, that first will still be there.
Are we allowed to use either of mine?
Yeah, we're allowed to use either of them.
So
Yeah.
maybe we can wrap them up, because so if you wrap something with eta with the modality.
Yeah.
If you wrap the then you can wrap it up, pass it around, return it as the thing, because inside the code you don't need to distinguish on what M is like.
Inside the code, we don't need to distinguish on what M is like. Yeah.
And
Yeah.
type checking, there's something about the
Yeah.
where the sea level comes in.
Yeah.
That it's, we can still use it for comparison.
Yeah. For
Yeah, so I think-
comparison.
Can we wrap it up? To be able to see?
Well, what we're going to do is we're just going to mark, like, so you can kind of think of sigma has like
Oh, that's
the
all,
thing,
yeah,
right?
that's what modality was replaced.
Yeah,
with.
so we
Yes,
kind of
yes,
have that
yes.
already, but what we need though is a level C that's distinct from top or bottom.
Yeah.
In order to exactly say what we want to. Right, and that's that's kind of what I wanted to get across with this example, right? I mean, there's other examples of where it's useful to distinguish between different levels, right? But I really like this one because it kind of hits Haskell programmers.
Yeah, and in the type of second,
Yeah,
that first, a compile time, that really matters. We do need that in order to type that.
yeah, exactly. Yeah. Time here. Oh, I'm over time already. Okay.
Yes, I'm afraid I've got to go on to another meeting, but I've really enjoyed this. Thank you very much, Stephanie.
Okay.
I'm going to say goodbye. And
Okay, Phil, I'm really sorry that I haven't gotten to the related work part yet. I will.
I may ask you that offline, and maybe even we can just, since you're at Edinburgh and I'm at Edinburgh, we can visit virtually during your trip. But I'll send you an email about that.
Okay, great.
Okay, thanks again. Bye-bye.
Bye, Phil. Yeah. So I'm going to skip these slides. If I want to mention just a tiny here, because Bob's here, of related work, if that's okay. Just to point out that I haven't really seen this level of precision in a type system for irrelevance, right? So I see type systems that are really good at runtime irrelevance, and I see type systems that are really good at compile time irrelevance, but not many type systems that do both at the same time and do them differently, right? So we have some that do runtime and compile time irrelevance, but they don't really separate the two, right?
Literature is full of profound ignorance in this matter. Not being this ignorant.
If I'm wrong, if there's something I missed, definitely let me know. about it. Yeah. Okay, so if you want to see the cursor here, these slides are also at this GitHub repo, and you will also find a link to our ESOP paper at the GitHub repo if you want to find out more about this. Also happy to talk about it much more. There's lots to expand on this in terms of, semantics or equality that takes types into account. Or we now have a dependent type system for DCC. Maybe we can do some proofs about non-interference in that type system. Lots of fun future work that I haven't done yet. Okay, thank you.
Interesting. Stephanie?
Yeah, thank you.
Yeah, so I have time for maybe two quick questions or one big question. Speak from the room.
Yeah.
I wonder whether this system is an instance of the multimodal type theory.
Multimodal type theory.
Correct, so, and I was
Uh,
so quite a general kind of, you have this, you can set up a whole kind of family of modalities.
yeah,
Yeah.
most of the dependent modal type theories have a big difference in their treatment of pi than this system. And that's on the slide that I skipped. But let me see if I can just explain what that difference is. Well, it really is, if you look at the pi rule, right, I mentioned that this label on the variable is only about the lambda,
yeah,
and not about how it appears in the body, right? So see how when we type check the body of the pi type, we use L, not L naught. Most of the modal systems make a really strong connection here, right? And they keep L naught the same in the body of the pi type as in the term that has that, right? And that's too restrictive for me, because then that's going to rule out things like homomorphic identity function. And there's some systems that kind of, well, I can talk about it later more, but like there's some that kind of relax it a little bit, but it's not as general as I want it to be. Right. There's also other systems that, so like Dominic Orchard and Harley Eves and maybe others have this other system where they actually have two labels on pi type, one to talk about what happens in the function, one to talk about what happens in the pi itself. That gets pretty complicated though, managing those two double labels and talking about how they relate to each other. Right, so I feel like the system kind of has hit the sweet spot. It makes a couple compromises, which I haven't really talked about why it can get away with this, but I'm really happy that it can.
There's a quick question on the chat.
Yeah.
Do you have use cases where the lattice is not linear, so not a total order?
Those use cases would be, say you want to do security types and you have lots of different kinds of runtime things and you have a big security lattice for that. In terms of irrelevance and not in linear order, not really, right? And that would be going back to the question of, would it make sense to have things that are not erasable, but you could ignore for equality? And I haven't really identified that.
And another one, have you seen the higher ranked polyvariant DCC, the case of 2020?
Higher ranked polyvariant? No, I haven't seen that. Yeah.